Welcome everyone, and welcome to this discussion meeting. I'm delighted to welcome fellows and visitors to this as our fourth discussion meeting of this current year, this session. And the paper we're discussing is parameterizing and simulating with causal models, from causal models. So we have people here at Errol Street, but we also have people online, so welcome to you as well. The session will be recorded, and the recording will be put on the RSS YouTube channel. If anyone doesn't want to be recorded, then please tell us and we can edit you out. Just for the people online, if you have any technical problems, then please use the support chat box and wait for someone in our support team to help you. This is a discussion meeting, so we actively encourage everyone to join in the discussion. We have an open session after the presentations, and it's interesting to note that all comments can be written up and submitted for publication with the paper in the journal, which is a good thing. The format of the meeting is presentation of the paper by the authors, followed by a vote of thanks by a proposer and a seconder. Then there'll be a discussion comments from those who've already asked to speak, followed by an open discussion, which we invite people from the audience here and online to ask any questions. And then we'll read out written comments that we have already received. And finally, the authors are invited to respond if they wish to the things that have been said. So that's the sort of format of it. I have to just comment that about the health and safety, that we haven't got a fire alarm scheduled. So if there is a fire alert, then we have to dash out of the doors that way and assemble on Errol Street corner, which is just there. And we have a fire marshal there, Judith, who will look after us and make sure that we all get out. So just to take note of that. Okay, so without further ado, just to say this paper will be presented by the authors and published in the Journal of the Royal Statistical Society, Series B, next year in 2024. Okay, I'd like to call upon the authors to present the paper. Firstly, Vanessa Diddley, and then Robin Evans will follow after, I think that's right. Okay, over to you, thank you.
Thank you very much. How can I point with this? How? Sorry.
It's on my laptop.
It's your mic.
Okay. Okay. Thank you very much. It's great to be here. Robin and I are very happy and very honored to present this work here at the Royal Statistical Society. And it's great to see so many of you here, and I assume there will be at least 200 people online. So we will show how to parameterize and simulate from causal models. Now, why isn't this trivial, you will say? And well, in fact, it isn't trivial. People have struggled with doing this for over 20 years, and now we can finally solve it. So in fact, it was in some work that I was doing with a PhD student of mine, where we were struggling to simulate from a desired causal model, and we didn't solve this to our satisfaction. So I went to Robin and I said, look, you know everything about marginal models. Can we solve this? And this is how this work started. So the plan for today is I will take you a bit through the motivation and why this isn't a trivial problem, and talk about the key ideas that we use for marginal modeling to solve the problem. And then Robin will take over and explain the Frugal parameterization, the main results, and then also how we simulate from these models. With the other applications, you will see that the potential for the application, for the use of this approach, is what we think is quite wide and far-reaching. So let's start with the motivation. Let's consider this causal graph, this causal structure, which will be familiar to many of you. This is the typical test case for estimation of sequential treatment effects. So in this situation, we have A and B as our sequential treatments. So first treatment A, another treatment B, and something might happen and be measured in between, Z, like whether the patient is doing better or not, and then we adapt the treatment. And at the end, we measure our outcome Y. Z and Y can also further depend on unobserved variables or factors like the underlying health of the patient. And now, obviously, from such a causal graph like this, it would be easy to parameterize and simulate from this by using all the conditional distributions that are induced by this graph. But that is not actually what we want, because we are interested in interventions on A and B in certain strategies maybe, and it's the distribution of Y under these interventions in the treatments A and B that we are interested in. So we want a nice model for the interventional quantity Y given we intervene. We're using Pearl's-Do notation here. So we intervene in A and B. And we might want to evaluate treatment strategies like always treat, A is equal to 1, B is equal to 1, versus never treat, both are 0, early treatment, 1, 0, and late treatment, 0, 1. Things like this. And we want a nice interpretable model for this. So let's remember why this is a difficult problem in the first place, or why it's so important to be able to simulate and address this test case here, this typical test case. It's because naive methods of trying to estimate the effects of A and B on Y, the joint effect of A and B on Y, will typically fail. One naive approach would be to do a regression of Y on A and B on the treatments, but then we are ignoring the confounding of Z by Z of B and Y, so the later treatment and the outcome. So that doesn't work. And another naive approach would be to regress Y on A and B and Z. But again, that also doesn't work because we are then modifying or breaking the indirect causal path from A to Y via Z by also conditioning on Z. So that's not good. And there's a second problem relating to including Z. That's that it's a collider, graphically speaking, a collider on the path from A to U to Y, and conditioning on Z then induces a non-causal association. It opens this path, it induces a non-causal association, which further mixes up the effect of A on Y. So none of these naive methods fail. We need to do something more clever, and it's the more clever methods from causal inference that we might want to evaluate and simulate from. So this structure is known as time-varying confounding by Z, because Z is a covariate that's affected by past treatment and affects future treatment. So it's also more aptly maybe known nowadays as treatment confounder feedback. So we want to be able to deal with treatment confounder feedback, and we want to be able to verify whether suggested methods really do this. So we want to be able to simulate from this. We know that in this situation, under standard assumptions, positivity, causal consistency, conditional exchangeability, we can identify our causal quantity of interest non-parametrically. We can look at it from two sides. One side is to use inverse probability weighting. So the inverse probability weighting deletes the incoming edges into A and B. We've omitted baseline covariates here, so there's nothing much to say about A, but the incoming edges into B by dividing by their probability. So this is why it's inverse probability weighting. So it's like analytically deleting the incoming edges here. But as we can see, and as many of you will know, this is non-parametrically equivalent to the G formula, because the remaining factors, after dividing by the two treatment probabilities or treatment distributions, the remaining factors are the conditional distribution of Z and conditional distribution of Y given their paths. And this leads us to the G formula as the identifying formula. And we still need to integrate out Z, which we are not specifically interested in, because we want the effect, the joint effect of A and B, or an intervention in A and B on Y. So this leaves us now with these options that relate this complex joint causal structure on all the variables to the left-hand side in this equation, so the interventional distribution of Y, which we ideally would like to be a nice interpretable model, like a logistic regression or a Cox regression. While the middle part with the inverse probability weighting is used for fitting, the right-hand side, the G formula, is suggestive of generating data from these conditional distributions, but it will usually not be the case that if you choose nice conditional distributions for Z and Y, that you get a nice expression for the left-hand side, for the interventional distribution on the left-hand side. And these quantities, or a nice model for Y given intervention in A and B, these are known as marginal structural models. That's what marginal structural models describe. They are marginal over Y, and they are structural because they are models for the outcome under interventions. And these marginal structural models are very popular and have been very popular and used a lot in epidemiology for over 20 years now, because in epidemiology, it's typical that we have time-varying treatments, and therefore we have time-varying confounding. And using marginal structural models and inverse probability weighting is almost like using a usual regression approach after a pre-processing step where we reweight our data. So, and in this reweighted data, we have that then the treatment variables are independent of the prior covariates. So it's a simple principle, and that's why it's also very popular. There have been many applications. One of the early motivating examples was the treatment, antiretroviral treatment of HIV patients, where the CD4 count acted as the time-varying confounder. And there have been many more applications since. So recently, for example, Ruth and colleagues looked at treatment strategies for cystic fibrosis patients. On my group, we looked at cancer screening attendance and its effect on mortality outcomes, or assessing side effects of drug use and interacting drug users, for example, in type 2 diabetes patients. So long history of using and applications of these marginal structural models, for example, in epidemiology. It's therefore interesting and surprising to see that when people simulate or want to simulate from these models, and I don't need to tell you in statistics, we want to simulate from models in order to check our methods, how do our estimators behave in finite samples, etc. And even though every model is wrong in the real world, we want it to be right in the simulated world, right? So, so it's surprising that a simulation is usually done in some indirect way. And these authors, they've done it in the correct way, but in an indirect way. So there's a series of papers by Jessica Young where they work out, they characterize when certain models coincide, like marginal structural Cox model and an accelerated failure time model, and that then makes it easier to simulate from the marginal structural model. On our own work, this was what I mentioned earlier, that motivated for me this work. We simulated directly by inverting the distribution function from the desired marginal model, but we couldn't make it fully work, and we had to modify the structure, the time-varying confounding structure, which was not very satisfactory. And in recent work from Ruth and colleagues, they have actually worked out in a lot of detail, if we specify the fully conditional hazards in survival settings with additive or Cox model, what are the implied marginal structural models, and they're not entirely nice. Some of it is quite intractable. So as you see, simulating from marginal structural models is hard. These approaches all do it in an indirect way, but what we really want is to specify a simple, nice marginal structural model, be able to simulate from this while retaining this complex confounding structure in our observational data. And it's been noted before, Jamie has known this for many years, of course. He noted the difficulty in performing likelihood-based inference because the likelihood of marginal structural models is a computational nightmare. Specifically, it's also difficult to identify particular causal hypotheses from these likelihoods. And speaking of hypotheses, let's remain with this example and assume we are specifically interested in the situation where A has no causal effect on Y. So as you can see from the graph, this will happen when there is no direct or indirect pathway, then it will have no causal effect on Y. But also we can imagine a situation where the two cancel each other out. So there's maybe a positive biological effect, but a negative effect via side effect or adherence to the drug or something like this, a negative indirect effect. And this cannot always happen if we go about the parameterization of these models in a not so clever way. This is known as null paradox because we can't identify particular null hypothesis. So this was described by Jamie Robbins and Larry Wasserman, again, more than 20 years ago. They say that if we specify seemingly nice parametric models for the distribution of Z given A and Y given A and Z and B, it might make it impossible for the null hypothesis to hold. Very simple models here, Z being following a logistic regression, Y following a linear model. Then we can work out here now the implied marginal structure model by integrating out Z. And we can see the null hypothesis that A has no effect on Y would mean that in this expression we must have no dependence on A. And for general A, this will only be true if the parameter beta A is 0 and either alpha or beta Z are 0. And then the expression doesn't depend on A. But these two conditions, they mean that Y is then either conditionally independent of A and Z together, or Z is independent of A and Y is independent of A given Z and B, which are much more restrictive. So that corresponds to really the two paths disappearing. So that's more restrictive than the null hypothesis that we are actually interested in. So the lesson is just specifying these nice conditional models is not helpful when we want data under a specific causal hypothesis. There are other problems with further approaches that you can find in the literature. We find this, for example, in mediational models or in history-adjusted marginal structure models, where the models are in fact over-parameterized, which can lead to non-congenial models. So just to give a very simple example, not particularly motivated by a causal model here, if we assume that there's a logistic, or that there's a, if we assume a logistic model for how Y depends on A, and a logistic model for how Y depends on A and B, these can't both be true because the logistic regression is not collapsible, at least not in generality, this can't be true. So there are several problems with this, and this is also something that we want to avoid. So this brings me now to what are the objectives of our proposal. We want to find a parameterization that describes the joint distribution of all the variables so that we can have an interesting relevant causal structure, confounding structure, but it should obey a given explicitly provided parameterization of the causal functional. It should allow the rest to be as flexible as possible, not imposing any further restrictions, and it should remain coherent and unambiguous. It should be possible to have these models shouldn't contradict each other, and they should fully specify the distribution. And then in a second step, of course, we want to use this to simulate from such a model, obtain samples so that we can mimic both the observational case, where we have the complex confounding structure, and the interventional case, where we have hopefully a nice pre-specified causal model. And as a third benefit on top of this, because we will have a fully specified likelihood, we can then also fit these models using likelihood-based methods, Bayesian maximum likelihood, and compare these to the more common semi-parametric methods that are typical for these marginal structure models, or also nested structure models. So a little bit, just very roughly, the idea of what we're doing in terms of the marginal modeling approach. Let's first define the P star notation, which is it allows a little bit more generality than with the interventions. But in this case, the P star is just the interventional distribution intervening in A and B. And as before, this factorizes well, in the way how we use it for the G formula. Now, the marginals in this distribution, so the marginal Z and the marginal Y, always given A and B, and the P star, what do they look like? Well, the first one, P star of Y given A and B, that's the model that we are interested in, that we want to specify. We want a nice, simple model for this. And the second, the marginal of Z under P star given A and B, that can be seen to just simplify to the observational conditional distribution of Z given A. We can see that from the graph or also from the formula on top. So that's a restriction that we want to be able to impose. So we have these two marginals, and what do we need now to fully specify the distribution, where we need something like a dependence measure, conditional dependence measure given A and B under P star. And we want this to be general and flexible and not somehow restrict the model any further. The only restriction we want is on the P star of Y given A and B, but not in this dependence measure. So typical choices or ideal choices would really be the conditional odds ratio. It has nice properties, but it's not really feasible when we have continuous values, when Z or Y are continuous. So in this case, we suggest using copulas. So these are the main ingredients, and Robin will tell you much more in a minute about the how we use this and the technical details behind this. So just to recap a little bit, we have seen that there is a tension between three things. The simple specification of the joint model allowing us to simulate and allowing likelihood-based inference. Is in contrast to the simple specification of the actual target of inference, in this case P star, which we want to be nice and interpretable, and also enforcing marginal constraints on the causal model, so which was that Z had to be independent of B given A on the previous slide, for example. And so we think that our proposal, using what Robin will define as the frugal parameterization, resolves especially the last 2 points, and hopefully doesn't make the first point much more complicated or too complicated. And at this point, I hand over to Robin.
Thanks very much. So just before I start, my younger daughter has managed to give me a cold 2 days before a very important presentation. So if I dissolve into a coughing fit, that's why. So so I'm now going to talk a little bit about the main definition that runs through our paper, which is called the frugal parameterization. And what we're going to do is to just divide up into the variables in our system into 3 different categories. So first we have treatment and effect modifiers. So they're everything that's going to appear on the right-hand side after the conditioning bar of the quantity that we're interested in. Then we're going to have outcomes of interest, and they're everything that's going to appear on the before the conditioning bar in the quantity that we're interested in. And then Z is going to contain the other covariates, maybe time-varying confounders or something else that we don't want to be in the quantity of interest at all. And importantly, these can all be vector valued. So we saw before that there were 2 treatments. So X in that case was the vector consisting of A and B. And there's no strict causal order either, because, for example, we had a treatment that was before our intermediate outcome Z in that example, and another one that was subsequent to it. So there's no particular causal order that has to be imposed on the system. And the object of interest is, as Vanessa was sort of saying, it's this P star of Y given only the things in X. So Z doesn't appear anywhere. Okay. And obviously, we need to be able to take a margin, but the margins we take are not standard margins, right? I'm not just integrating out. I have to do something else first. And in order to be able to express that in a flexible way, I'm going to use these kernel functions. So a kernel function is just a conditional density. In this case, it's going to be a conditional density for our variable z, the ones we want to get rid of, given our treatments and effect modifiers, x. So it just satisfies two properties, that it's non-negative, and for every value of x, it integrates to 1 over z. And it can be a smooth function of the marginal density of everything before our outcomes, if we want it to be. And what we're going to do is to define a p star to be cognate to the ordinary conditional of p of y given x within the joint distribution that we're interested in. If we can take the full conditional, so that's p of y given x and z, multiply it by this kernel function, which has to be a smooth function of the margin that would normally go with that conditional, and then integrate out z, and that's how we get our quantity of interest. So provided that you can write the quantity of interest in this form, then you can use our Frugal parameterization to simulate from it. And we can sort of think of this quantity inside the integral here, the integrand, as being our joint p star distribution. So it's sort of, this is a sort of implicit way of constructing the p star that we're interested in. So we reweight our distribution with this w function here. Okay, so that was a little bit abstract. So what kinds of distributions are cognate? Well, mathematically, you'll be reassured to know that p of y given x is indeed cognate to itself. So if we put in the ordinary conditional of z given x as our weight function, our kernel, then it will just give us out p of y given x. So that's a reassuring for any mathematician. The identity function is included in our proposal. We can also have the backdoor formula. So you see the second example there, which goes with this graph at the top here. If we just put in the margin for z, then we get here the causal effect of x on y, the marginal causal effect of x on y. And we can do something more like what we had in our previous example. So here we've sort of relabeled everything. So c would correspond to a, x would correspond to b, and we can have this sort of G formula-like expression where the weight function is the distribution of the covariate given just the effect modifiers, but not the treatments that come afterwards. We can also have slightly more exotic things. So if I put in the marginal for z, but conditional on a different value, which has to be fixed, then I can get things like this distribution of a potential outcome with a particular setting of x, which will vary, conditional on a factual value of x, which is some other value, x prime. This x prime has to be fixed, and it's the little x that varies in the cognate distribution. And this means that we can include things like the effect of treatment on the treated, because we can use this distribution to compute this expectation here. So we just set little x to be 0 and x prime to be 1, and we would get this counterfactual, which is expressing what would happen to people who factually received treatment if they had not been treated. Okay, so that leads me to my definition now. Finally, the Frugal parameterization consists of 3 separate smooth and regular parametric models for what I call the past. So that's the distribution over the covariates and the treatments and effect modifiers. The distribution of interest, which is some distribution that's cognate to the ordinary conditional of the outcomes given the treatments and effect modifiers. And then a dependence measure, which you can use to join together the outcomes with the covariates in a way that does not place any restriction on their margins. So these quantities are very nice because they specify the whole distribution P. The first 2 quantities are always variation independent because the variable y does not appear in the first piece. But if we choose the dependence measure to be, for example, a copula or a conditional odds ratio, all 3 pieces turn out to be variation independent of one another. And they also don't have any redundancy. So there's no suggestion that we're specifying the same quantity in 2 of these bits. And then our main result basically says, if you can do this in the ordinary distribution, so if I can do it with the ordinary conditional distribution and the sort of isomorphic quantity in the original distribution, then I can also parameterize it in the causal distribution that's specified by the kernel that I choose from the previous slide. So basically, if I have a smooth parameterization of P with these three models, so the past, the ordinary conditional of y given x, and the dependence measure, then I can do the same thing in my causal distribution and get a different smooth parameterization of, again, P. And as we say, if I can choose the parts of the second list here to be variation independent if I want to, and then the same will be true of the components of the first list as well. So this gives us the best of both worlds that Vanessa alluded to earlier, where we get a coherent joint distribution and we are able to choose the marginal piece, this P star of y given x, to be whatever it is we want. Okay. So let's show you that it actually works with some simulations, because theorems are all very well, but can you actually do it? So what we're going to do is show how we simulate from these models. So we start by simulating from the distribution after an intervention. So we start by simulating samples from P star, and then we're going to do rejection sampling to get back to samples from P. So we start by, with the model we saw before, where now B has been intervened on. We're going to assume that A and B are binary, and we'll sample them to be independent Bernoullis with parameter 1/2. Then we're going to simulate from the copula, so we'll get now quantiles for our intermediate outcome and our final outcome, and we're going to sample them from a Gaussian copula model with this correlation that's given here, and this is just a link function that makes sure that whatever value of A is, this will always be between -1 and 1, as correlation should be. So this could be any expression we want, but this is the one we've chosen because it just seems very natural. So that's great. So now we've got quantiles, but we want the margins to look correct. So we then use an inversion method. So we take the CDF that we want for Z. So we're going to choose this to be exponentially distributed with rate e to the 0.2a minus 0.3. And then we will then have Z distributed as we want. And we do the same for Y. So we want the interventional distribution of Y to, for example, be normally distributed with mean -1/2 plus 0.2a plus 0.3b and standard deviation 1. And at this point, we now have samples from our P star. But that's no good because what we wanted was samples from P. So we're going to do rejection sampling. So we bound the ratio of the distribution of P star of Z and X and P of Z and X, and perform our rejection sampling, and we choose B in this scenario to have this distribution here. So it's a logistic regression again, with parameter 1/2 for A and 1/2 for Z. And we can sample this using the R package Causal, which you would have all seen in the demo earlier, very wonderfully introduced by Xi and Dan. And we can take a sample of this of size 10,000 very easily. I invite you to download the package and have a crack yourselves. And given this data set, we can then start fitting the models and checking that it actually does what it's supposed to. So we could start with a naive regression model. We just pretend there's nothing causally interesting going on here at all. And we said earlier that if we do that, we will get a biased estimate for B because Z is a compounder. And you can see indeed here that the truth for B is 0.3, but our estimate is nearly 0.45. So the bias is very large compared to the standard error that the model has suggested it should have. Or we could do things the correct way. So we could use inverse probability weighting. So we fit a logistic regression for the model for B, given A and Z, which we know is correct. And then we inverse weight each observation so that it looks as though in the pseudo population they're independent. And in this case, when we do our regression, we get answers that look correct now. So the bias is now smaller than the standard error in every case. So this suggests two things. Inverse probability weighting works, and our method also works. That's good. What's also nice, as Vanessa mentioned, is that because we have a likelihood, we can fit using maximum likelihood estimation. So we did this, we just shoved it into Optim, and this time again we get estimates that look as though they are consistent, and the standard errors are slightly smaller than they were on the previous slide, which again shows that maximum likelihood estimation is indeed more efficient if you correctly specify the model. We don't recommend using this in practice, but it's useful as a comparator if you're doing simulations, because in that case, it's sort of an oracle estimate, right? It's the best you could reasonably hope to do, and it will tell you whether, for example, inverse probability weighting or doubly robust estimates are doing what you would hope. But if you have a data set, it's unlikely you will know the correct form of the model. Okay, and then we can do a lot of smaller simulations. So here are 1,000 data sets, each of size 250. We've estimated the parameters via 4 different methods. So there's the naive method in the top left, which you can see. So here we're plotting the bias, and the coefficients. The red one is the intercept, green is A, the sort of bluey one is B, and purple is AB. And you can see that the B coefficient is biased a little bit upwards. But the other 3 methods, that's inverse probability weighting in the top right, a doubly robust method in the bottom left, and maximum likelihood estimation in the bottom right, all seem to be giving unbiased results, and they have a nice spread. You might think this is a bit odd because surely maximum likelihood estimation should be more efficient than the other 2, but I think this confounding just wasn't strong enough. So if we increase the coefficient of Z in the model for B to 1 from a half, then you get a much stronger bias in the naive estimates, a little bit of bias still in the inverse probability weighting. And you can also see that the variance in the maximum likelihood estimates is lower. So there's not nearly so many estimates in the top range between 0.75 and 1. Okay, so it works, that's great, but that's not all you can use it for. So there are lots of other approaches which I think will be very important in the future. The first one is to survival analysis. So this is one of the original papers I was looking at considering this, was by Young and Chekgan, and they use sort of very intricate methods for simulating from discrete time Cox marginal structural survival models. So the idea here is you want to specify a model for the probability of surviving to the next time point, given that you've survived so far, and you intervene to fix all the treatments to particular values. And the setup here is we've got a series of treatments, A1 up to AT, some time-varying confounders Z1 up to ZT, and outcomes Y1 up to YT. And we can allow for a hidden process U1 up to UT, provided that it doesn't have any edges into the treatments. And essentially, this resolves an open problem in the literature because, as Vanessa was saying earlier, there have been various efforts to simulate from these Cox marginal structural models, but it's very hard to do it directly. So what's particularly nice about this is it makes it very easy to specify a null hypothesis. So if I, for example, think the treatment doesn't have any effect at all marginally, I just set this piece to not depend upon the treatments, simulate, and then I can test some method which tries to reject the null hypothesis, check it has the correct size, for example. And I can easily incorporate something like a stationarity assumption where it doesn't matter what time point you're at, your probability of survival only depends upon, for example, what your last treatment was. And just to emphasize why this is great again, in that paper, Young and Chekgan say this is not at all trivial, right? So they say we therefore may be limited to simulation scenarios with the proposed algorithm to unrealistic settings. And our point is you don't have to be restricted to those. You can have any distribution of static covariates, any distribution of time-varying covariates, any distribution of treatments, any distribution of survival, any dependence, provided that you specify this piece in the top left here, then everything will work. Another example, which I might skip in the interest of time, is sensitivity analysis. So because we can control the propensity score, we can, for example, evaluate what happens if we misspecify that. Another use is what I call many data, which is where we have lots of different studies, all of which maybe have information about a particular causal quantity that we're interested in, and we can integrate the analysis of all of them by having a single parameter that's common to them all. And we could then use some score, maybe the likelihood, maybe something else, to estimate that using all the data pooled at once. And this is a paradigm I call many data, by analogy with big data, right? So instead of having one massive data set, you've got lots of data sets which may or may not be large, but they're all telling you about the same thing. And in a recent paper, she and I have described a way to do this with a randomized control trial and a large observational study. And the final sort of application I'm highlighting here is fitting models that have what we call nested conditional independences. So the story here is, if we consider the model which looks rather similar to the one we've been considering all along, where now there's no edge from A to Y, and that implies the constraint at the bottom. So it says that this distribution that we're considering, P of Y given do A and B, doesn't depend upon A. And it's identifiable because obviously you can do the intervention on B probabilistically and check whether or not this holds. And what's nice is that now we can explicitly fit this model with and without the constraint, and then just do a likelihood ratio test to see whether the data support the constraint or not. And that's, again, something we just couldn't really do before. Okay, so to summarize, we presented this Frugal parameterization, and we've used these methods from marginal modeling to simulate from causal models, and we can also fit these models using likelihood-based methods. I want to emphasize this is a marginal parameterization, and lots of causal models that are of interest are marginal, and the marginal modeling literature is very old, so there's probably lots of other interesting things you might be able to go and find yourselves to help you with your own causal problems. So I encourage you all to go and have a go at that. So we envisage applications to marginal structural models, which we've discussed in some detail, survival models, which I've mentioned briefly, dynamic treatment regimes, structural nested models, which are in the paper, stationarity and transportability. So stationarity I mentioned, transportability, I guess that's sort of related to the data fusion, many data thing I was talking about earlier, and sensitivity analysis, again, I didn't have time to chat about. So I think in sum, it should be, it may well be applied to a very wide range of scenarios. We can also simulate from arbitrary instrumental variables models using this method, which doesn't seem to be something that anyone has ever tried in the econometrics literature. So that's another project that's in the pipeline. So there are some limitations. Unfortunately, it does not solve every single problem. So mediation models are still very difficult to simulate from, and that's because the sort of standard way you might do non-parametric mediation is you imply that you split your treatment into two values, which observationally are always the same, but you want to know what would happen if you could change one of them. The problem there is that you have to enforce a conditional independence that conflicts with the parameter you're interested in. So you effectively end up having to try and specify the same thing twice, which is very much no-go in terms of the Frugal parameterization, because it's Frugal, right? You can't do that. Continuous outcomes generally rely on this rejection sampling, and obviously that does not scale well. So I showed you some low-dimensional examples where it worked very nicely, but in higher dimensions, it becomes exponentially slow as you add more variables to simulate from the data. Fortunately, we have found a solution to this, which is to use inversion, which was found by Xi, and this makes the thing a lot faster. So now it's only a linear complexity in both the number of variables and the number of samples you want. So that's no longer a problem. I think that's everything I have to say. Look forward to the discussion.
Thank you very much to both speakers. I'd like to now call on Sean Seaman from University of Cambridge to propose the vote of thanks.
Right, this one.
Yeah.
Okay, hello everyone. So I'm very pleased indeed to be proposing the vote of thanks for this excellent paper. Although I am uncomfortably aware that most of what I'm going to say relates to problems that the authors have already solved, as I've discovered today. So let's see how we get on. So I found this paper to be utterly fascinating and very, very thought-provoking. It's useful for simulating data for simulating data for your simulation studies, and for doing maximum likelihood estimation and Bayesian analysis. And I particularly like the way that the authors consider in depth two particular examples shown by the diags there, but they also sketch how to deal with much more complicated settings. And reading and thinking about this paper made me realize how I could do two things which I hadn't been able to do previously. One of them was to simulate data from a particular structural nested model that I'm particularly interested in for survival time data. And the other was to, and this was work I did with Ruth Keogh, how to simulate from a Cox marginal structural model without having to impose certain restrictions, which Robin's already mentioned. I mean, I might be just repeating what you've already heard, but this is my understanding of the basic idea. So I'll take the author's first example, which involves the exposure X, a confounder Z, and an outcome Y. And their proposal for simulating data from that model, or consistent with that model, I should perhaps say, is that you specify the joint distribution of the variables when X is randomized. And so when X is randomized, there's no confounding, and the blue arrow from Z to X disappears. So they say, specify the joint distribution in terms of the following components. So the conditional distribution of Y given this randomized X, and because X is randomized, that's the same as the conditional distribution of Y given that you intervene on X and set it equal to X. So that's the causal model, that's the model you're interested in. Also, you specify the marginal distribution of X. So X is randomized, so if X were binary, you might, for example, just say that X is Bernoulli with probability of half, for example. You specify the marginal distribution of the confounder Z, and then you have to describe the association between the confounders and the outcome when you intervene and randomize Z. And then the idea is, I believe, that you obtain samples from this distribution, which is not too hard, and then you use rejection sampling to get samples, to subsample from this sample that you've just obtained, subsamples which represent a sample from the observational distribution. So that's the distribution where there is confounding, where that blue arrow from Z to X does exist, is operating. And the rejection sampling step involves taking each of your sampled individuals and accepting them and saying, this represents an individual in sample from the observational distribution, doing that with probability equal to this ratio here, which is the probability of X given Z when X is not randomized, divided by the probability of X when X is randomized. And as has been commented, this is basically the opposite of doing inverse probability weighting, which you might use if you were going to analyze observational data. Because if you were doing that, what you would do is you would weight each of the individuals in your observational sample by the inverse of this quantity here. So you, as I say, you're just doing the opposite of inverse probability weighting. Okay, so I've got some questions, at least two of which have been answered already today. So the first one is rejection sampling needed? The second one is, how do you use copulas when there are multiple confounders? And the third is, why is maximum likelihood useful? And the third one, I think we can probably skip because, it's useful because you want to compare, although you might not want to use it in practice to fit these models, you might want to know how efficient a semi-parametric method is compared to when you're prepared to specify all these extra models that are needed for maximum likelihood estimation. Although I would mention that presumably the relative efficiency of the maximum likelihood compared to the semi-parametric method depends on how much you saturate your extra models that you need for the maximum likelihood. Because ultimately, if you do saturate them, presumably you end up with just the same answers, I'm guessing, as the semi-parametric method. Okay, let's look at questions 1 and 2 anyway. So question 1, I'm going to bore you now because you got this during the demo. So 2 of the examples in the paper show how you can sample from the observational distribution without needing a rejection sample. In one of them, all the variables are normally distributed, and the other one, they're all binary. And my question, which has been answered, is, can't you always do this? And so I'll take the first example with x, z, and y, and suppose that they're both univariate, as is in the paper. And suppose that we choose to use a Gaussian copula to describe the association between the confounders and the outcome when you intervene on x. So this is what you do if you want to sample from the joint distribution of the variables when you intervene on x and set it equal to little x. So the authors say, specify a marginal distribution for z, which is important to notice is the same as the marginal distribution of z when you intervene on x, because x is prior, sorry, z is prior to x in the DAG, z is prior to x in the DAG, so changing x won't change z. And you also specify a marginal distribution for y when you do intervene on x, and some association parameter rho. So we're using a Gaussian copula here. So how does that work in detail? Well, first you sample 2 random variables, wz and wy, from bivariate normal, which is standard normal, except that you have this correlation gamma. And then you apply the cumulative distribution function of a standard normal to each of these w's to obtain u, z, and uy. And the thing is that the uy and the uz, they're both marginally uniform on the interval 0 to 1, but they're correlated because rho isn't, assuming rho isn't equal to 0. And then you take uz and you apply to it the inverse of the CDF of z, which is whatever you specified its marginal distribution to be. And you do the same thing for y, and the result is that x and z are both samples from the required marginal distributions that you specified, and they are correlated, which is what you wanted to achieve. Now, alternatively, and this might be useful when z is a vector, you could do this instead. It's very, very similar. It's just a sort of different order of doing things. You sample z from its marginal distribution. You calculate uz that corresponds to z. And then, and this is what was mentioned in the demo, or at least the next slide is about what was mentioned in the demo. You sample uy given uz from the conditional distribution that's implied by this copula that you're assuming, this Gaussian copula. That's quite easy to do because there's because wy given wz is just a normal distribution. So you've got this simple relationship between these two things. And then you calculate, just as before, you calculate y from uy. Okay, now this also works if z is discrete. I've presented it here as though z is continuous, but you need a small modification if z is discrete. Okay, so in the paper, I know things have moved on since then, but in the paper they propose doing that where x has been sampled from some dummy distribution, and then using rejection sampling. And so what I'm describing here is what was described in the demo. You sample Z and X from the margin, from their observational distribution. You calculate UZ from Z, and then you sample YZ from its conditional distribution given UZ, and then calculate Y. And there's no rejection sampling needed there. And you can do this with I've just done it with the Gaussian copula, but you can do it with many other copulas, and not all copulas, but for a lot of copulas, this conditional distribution that you need is known. Okay, you can do the same thing. I won't go through this, but you can do the same thing for the second example. And in fact, Ruth and I broadly use this approach in writing the paper that we've submitted and put on archive, which takes Robin and Vanessa's ideas and exploits them to describe how you can simulate from a Cox marginal structure model more generally than is in the paper, without requiring restrictions. Okay, so second question, I'm not sure whether this one's been answered. So this is about how do you use a copula when Z is a vector in this example, or in the second example where L is a vector. So there are multiple confounders. So my understanding is that in the paper, it's recommended to use Vine copulas, and in Appendix C, Robin and Vanessa go into quite a lot of detail about how to do this. And my understanding is it involves specifying univariate marginal distributions for each of the confounders individually, and then specifying some bivariate copulas to describe the association between these various confounders, and some bivariate copulas to describe the association between the confounders and the outcome. And I'm just wondering, would it be easier to just specify the joint distribution of Z, however you want to do that, and then choose a scalar function, H, which you could think of as a summarizing function, perhaps summarizing Z. Choose this function, and then calculate the univariate random variable H by applying the function to Z, and then finally describe the association between Z and Y by using by specifying a bivariate copula to describe the association between this summary measure H and Y, given intervention on X. That just seems to me easier to do if your aim is to simulate data. The summary measure, by the way, the summary measure might be something as simple as just the sum of the X's. It depends on what scenario you're working in. Right, we've done that. Okay, so in conclusion then, I learned an awful lot by reading this paper and thinking about it. I think it's a wonderful paper. Now we can simulate data so that our causal models are correctly specified. Now we can do maximum likelihood and Bayesian inference. And so it's with great pleasure that I propose the vote of thanks.
I'd like to call on Ricardo Silva, University College London, to second the vote of thanks. He's actually going to contribute remotely. Over to you, Ricardo. Thank you.
All right. I got it. Everybody can hear and see me. So I'm really sorry for not being there in person. I'm feeling under the weather and a bit cranky of a headache, so it's better to give some distance. Very grateful for this opportunity of commenting Robin Vanessa's paper. It's a paper which I liked very much. I'm not sure, can you see my screen? It disappeared from. Can you see my screen?
Yes.
Yeah, good. I cannot see it. So I appreciate this paper very much to the advances they do to likelihood-based inference. particularly where it demonstrates how it's applicable to multiple families of causal models that people do care about in practice. My main comment is about the different ways we could frame the results, because I think this is of relevance to both practitioners and methodologists. So what do I mean by this? So I'll take as an example structural causal models, which are kind of get a bit of a criticism in the paper because there are things you'd like to express in models that imply some constraints that are not quite clearly expressed in structural causal models. But my case here is that sometimes when you look at this paper, they don't really exploit this methodology in full generality. I hope to illustrate some of these cases here. In particular, I'll show how we can frame some of the results from Rob and Vanessa in applications such like modeling the effect of a particular intervention, multiple variables at the same time, and issues of partial identification, framing some of the ideas in terms of structural causal models. I won't be able to say much about simulation, I'm afraid, because time is limited. So let me discuss this via some examples. Let me start with this one. Here's some treatment X, some outcome Y, able to block confounding with some cover Z. If you were to think of a system like this in terms of a structural causal model, where they have a system of structural equations like this one relating Y to these variables X and Z, and some latent background vectors UI. So you have vectors for each one of these variables there. But the goal is not to worry about that, but model the effect of X on Y directly. Z is there just to be able to achieve identifiability by condition ignorability. So how can you do this? I mean, it's we know for ages that you can use structural causal models as a constructive procedure to define a joint distribution of potential outcomes. So one way of understanding this is you think a potential outcome over Y having a distribution that is like the push-forward measure that you get from propagating the uncertainty on UI as defined stochastic process that is indexed by experience X and Z. And this stochastic process is just what you get from the structural equation, where you treat X and Z here not as realizations of random variables, but just as fixed design points. So because the source of randomness is the same for whatever you plug in as the index points, this defines a whole path in a stochastic process. But you don't need to use all the causal patterns of Y, right? And you know you can just, for example, fix X only and propagate whatever uncertainty is necessary to define a potential outcome on the intervention X only. And this is just again given by the structural equation problem or model where the role of Z is substituted by a function that depends on this other source of randomness, in this case, YZ. So if I have a system like this, I may want to keep the observable variables X, Y, Z, but I have the freedom to choose which latent variables to explicitly put in my model. So what I'm going to do next is marginalize UX, Y, Z, and keep Y naught and Y1 there. You get a graphical model like this, where this vertex in particular represents a stochastic process. So my notation in curly brackets just means here's a collection of variables. In that case, is Y naught, Y1 if X is binary. I know I can remove this edge from Z to Y because by consistency, if I'm told X, I'm told the potential outcomes, I know everything I need about Y. This essentially defines Y in terms of a structural equation that's expressed by these potential outcomes instead of some generic background variable UI. So it is true, as Robin Vanessa said in the paper, that you can think about a structural causal model, we have to think about marginal modeling, because each variable is modeled as a function of all previous variables and then some noise term. There is some determination here what we mean by noise term. I mean, I can mix and match the sorts of uncertainties to regroup my model in a way that is easier to do a marginal parameterization of some of the effects. So if I have a model like this, which for the lack of a better name, I'm calling a structural causal model with explicit potential outcomes, it's already moving forward to something that isolates Y sub X in ways I could parameterize the distribution marginally. So you can have here, for example, something that traces back the steps of Robin and Vanessa. You have kind of distribution of that test. I can define a copular process. I mean, this X here doesn't need to be discrete, right? It could be continuous, and then this potential outcome process is infinite dimensional. You can define a copular process too. And then you can define some marginal distributions for each one of these potential outcomes too, which can incorporate whatever families or constraints you may want to incorporate. So of course, this sounds horribly non-frugal, right? Because it's define a whole distribution of all joint potential outcomes, which may be an overkill if what you care about is, as is illustrated in some of the applications in there, a single word causal quantities, like the average treatment effect. Now, one way about to go around that is you don't need to specify a full likelihood function. If you think about the joint distribution in this case where X is binary, so that only two potential outcomes, you can have a fully connected joint distribution, so to speak, expressed as some sort of graphical model. And here my choice was to make it akin to a chain graph. So you have Z as the first layer of the chain graph, and Y0, Y1 as the second, where it specifies the conditional distribution of each one of these guys given Z. And you know I can define them separately, and there will exist a joint distribution where they fit together, no problem about that. But once I have this particular partial specification of my model, I can then flip, if I wish to do so, in terms of a marginal model. So substitute that by a coupler for each potential outcome in Z, and the corresponding marginal distribution. There's a kind of mapping the ideas of Robin and Vanessa data to this different language here. And to give a bit of a more complex example, let's apply the same ideas to the case of Havercroft and Diddlers. So if you are familiar with linear structure equation models, when you see a common confound like this, your first instinct is to think, well, if this was a linear regression problem, I would have correlated errors between L and Y. So the equivalent of that could be imposing putting a model the corresponding stochastic processes of the potential outcomes of interest. Here, if you want to model the effect of A on B on Y, you may choose this particular set of potential outcomes. So the edge from L and Y disappears too, because A and B and the potential outcomes determine Y. And you can model the dependence between these two sets of variables. But what you choose to put here as problem dependent doesn't need to be inspired by ideas from linear structure equation models. If you wanted to model joint effects of A not only on Y, but also on B, if you wish to do so, you could explicitly include the potential outcome process for B sub A. And the dependency structure you get could be could be created by following what you get from that expansion of the structure causal model in terms of the potential outcomes it implies. Likewise, if you just want the effect of A on A and B on Y, this is the only margin that you need to specify. And this is a secret mixed graph. It's just a set of potential outcomes shown explicitly. Excuse me. So if you want to parameterize that, so as a way of example, if I wanted to explicitly keep LA and explicitly keep the Y sub AB process, I could start from the same idea, fully connect them some way that is convenient. Here's again mimicking what you get from a chain graph. The LA process in one layer, the YAB process in another layer. And for the same game that I mentioned before, I can just use conditional distributions of interest, and here I'm keeping only those which are within a single word. So if I have little a in one column, I'm linking to little a on the next column. A prime connected to a prime only. And these distributions can be defined knowing that will exist a joint distribution accommodating them, because if you were just to drop this, the edges are grayed out here, this will define a whole joint model. So it will be enough to define these conditional distributions. And if you want to flip in a marginal model, I transform them into copulas and marginal distributions. Excuse me. So far, what I present has more of a translation exercise, following very closely what Robin and Vanessa did, but I do think this is worthwhile when trying to communicate to both practitioners and other methodologists who may want to build on it. But hasn't even come completely clear what you gain by this switch in terms of presentation. Of course, if you were interested in crossword distributions, then maybe you had to move towards this direction anyway. But many people may not care about crossword distributions. So what if I think about single word quantities, but in unidentifiable models? So this refers to the task of partial identification. Actually, in their paper, Robin and Vanessa sketched some ideas about instrumental variable models at the end. The way they do this is they include explicitly some latent variable in the likelihood and basically apply the ideas on top of that. I'm not too comfortable with this because there's a catch-all symbol for all sorts of latent causes you might have. It's literally unknown, right? Not only it is unobserved, but you don't even know what it is. And if you think about how you parameterize this model, there's some degrees of freedom that don't make me feel too comfortable either, because for instance, that could put all the randomness in that marginal PU and treat the condition of y given the others as a deterministic function. This is what is traditionally done with some approaches for partial identification, where this condition distribution is not only deterministic, it has no free parameters. So it's not a direction that I feel is the best way of approaching partial identification, at least, but you still can stick to the ideas of their paper, just expressed in a slightly different way. One way of doing this is following this construction mentioned. You choose your parents wisely. Here's the stochastic crosses of the potential outcomes, y sub x. You parameterize this in a relatively straightforward way once you know what the results of Robin Vanessa's papers, of course. You have this condition distribution of x given z. We have the separate copulas for x and each potential outcomes given z, and the margins of the potential outcomes. The type of thing I played with a few years ago with some collaborators when defining models for instrumental values where x is continuous, because there's nothing stopping us from treating this with a potential infinite stochastic process. You can cope with that when you parameterize this instrumental variable model like this. And the reason why this may be particularly convenient is because I think it's easier to think through which kind of models will be useful for this type of task, because even if you may have some unidentifiable quantities like this in your instrumental variable model, you may feel more confident which kind of families of probabilities you should be able to use there by mirroring what families of probabilities are convenient for observable quantities which you can estimate, like y1 given x1, x equals 1 and z. So if you feel some particular family is good for that, you may want to just borrow this idea to model the family distributions for these unidentifiable quantities, which at least for me is a nice way of thinking and trying to hammer together some factors that include unspecified latent confounder. There's nothing here when you use this partial identification that requires specifying a joint distribution of these potential outcomes. I mean, much of the classical work here in IVs put a distribution that joint of the potential outcomes, and you don't need to do that, right? You can just do that marginally too. So, in conclusion, as you can see, the main point I wanted to make actually refers to the final 2 pages of Robin and Vanessa's papers, which I think testifies to the strength of the results they present. I do think that what they're doing, the direction they're taking for identifiable models can work. Of course, they already presented some preliminary results on this, but maybe it's worthwhile investigating alternative approaches that share some of the DNA with what they present. And finally, I would like to say it's been a pleasure to read this paper. It's been a pleasure discussing, and I second the vote of thanks. Thank you very much.
I'd like to thank organizers for this wonderful opportunity to discuss this brilliant paper. So I just want to offer my interpretation as I read the paper, and some of you may find what I'm going to say rather boring, but I'm going to say it just in 5 minutes. So just bear with me for that. So when I read the paper, I think I find it a bit easy to interpret it in terms of 2 factorizations and a density ratio. So suppose we have this partition of a random vector as x and y and z. Now forget about the causal modeling for now. Just look at the observed distribution, P of z, x, y. There are two ways we can factorize the model. On the left, we have the usual way, right? The joint of zx and the y condition of z and x. And there is yet another way, as pointed out by the authors, that we can factorize them into three pieces, the zx, the y given x, and this copula or conditional dependency model, phi of z and y given x. So on the left is the usual factorization. On the right is the device used by the authors. So concretely, to think about this conditional dependency measure, we can use the conditional odds ratio. But for now, for concreteness, let's think of this as a conditional density, a conditional copula density. Then, given these three factors on the right, we can assemble them to parameterize our observed distribution in terms of this factorization, right? So zx, y given x, and this conditional copula density. So where does the causal modeling come in? Because we're not directly interested in the observed distribution, but rather we're interested in some distribution related to this. In particular, I argue that the relation can be in general thought of as a density ratio. So I would argue that the density ratio would satisfy three requirements. One, positivity. We require this strictly positive almost everywhere. So this ensures that the inverse of the density ratio is exactly the other way around, as exactly pointed out by Sean in the previous discussion. So also, we require the density ratio to not depend on the outcome 1. And finally, the density ratio should be identified from the observed data distribution. So actually, it follows that if we define the density ratio in such a way, the density ratio can be also identified from the P star distribution. So based on such definition, and if we arrange this a bit, we can derive the density ratio is exactly the ratio between the two margins of z and x. And also this P star y given x exactly coincide with the observed Py given zx. Okay, so I can draw the diagram in such a way. On the top, we have the two factorizations of the observed distribution, and on the bottom, we have the two factorizations, two ways of factorizations of the distribution P star we're interested in. In particular, we're interested in part of this P star, namely this P star y given x. That is the marginal causal model that the authors have been talking about. So more generally, we can think about parameterization as parameterized components we can pick from this diagram. In particular, the Frugal parameterization would correspond to this. So we have zx on the top and the other two parts from the bottom, both of them on the right-hand side. So just to rewrite, given this parameterization, how do we assemble the observed data distribution? So there are other examples that you can view it in such a fashion. For example, this is the graph, the Verma or the dynamic treatment graph. And we can also represent, so this is the P observed distribution of this graph. We single out this component, and this is the P star distribution correspond to the world after intervention on the right. And then we have these three boxes that would simultaneously parameterize P and P star. And this is a different parameterization, the structure nested model, where the density ratio is a constant. So actually, we can parameterize alternatively with components on the left. In this case, P of zx and P star y given zx. There is just another model, another case that, as illustrated in the paper by real data analysis, where sometimes we want to look at how a baseline covariate could modify a certain effect. In this case, we have baseline covariates Z has two components, Z log and C, where C is the component we want to study its effect modification. So that is, in other words, interested in modeling this Py do X given C. But in the meanwhile, we don't want to forget that C is a component of baseline covariate, and it could be inducing confounding. So we also want to control for C in our analysis. So we can basically choose the density ratio as P of X divided by P of X given the Z naught C. So the X given two components of my baseline covariates. And then I proceed as usual. I pick these three parts as my parameterization, among which this P of star Y Cx is exactly P of Y do X conditioned on C. That is the exact modification model that ultimately I'm interested in. So how does that relate to the author's definition of cognate distribution? So I would think that the cognate distribution corresponds to those choices of density ratio such that it is some kernel of Z conditional X divided by observed distributions Z given X. But I'll leave it as a question for the authors, whether formulating it in terms of density ratio is slightly a bit more general. So I want to congratulate both Robin and Vanessa. Thanks very much.
So we now move on to open discussion. I'd like you to encourage any comments from the audience here or online. We do want to note your details so that we can follow up with you, so that we can get hold of a written version from you to add into it when it's published. So please, if you make a contribution or comment, give us your name and your affiliation. We do have a question or comment from online, and so we'll start off with this person, please. It's Ilya Spitzer. If you'd like to make your comment, please. Welcome.
Hi, everyone. Can you hear me okay?
Yeah.
Yes. Great. Thank you, Robin and Vanessa, for a wonderful presentation and a wonderful paper that I've read with great interest. I just have one comment, which is sort of maybe related to Richard's presentation. So, you're doing marginal modeling, right? And it's all about how you're doing the associate, like you have a marginal model and some sort of measure of the way variables associate. And you use copulas, and I can see that there are some computational advantages perhaps to using copulas, but I get very worried with copulas. And specifically, I'm worried about extra assumptions that get snuck in if you do that. I'm aware that Ricardo had a sort of a paper from a while ago on parameterizing things with copulas where there were extra Markov assumptions, for example, from doing that, if I remember correctly. And so I was just wondering, and Vanessa made this offhand comment without really elaborating at the beginning that you thought about, odds ratios and you kind of thought they were not suitable. And I was just curious, I guess I have a twofold question. First, why was that not suitable for your needs? And two, what extra assumptions are we sneaking in if we do copula models to model associations between things in marginal models, the way you're doing it? Thanks.
Thank you. Thank you very much. We'll have the responses after the end of this part of the meeting. Any comments from the floor? Any questions that anyone would like to raise? Now's your opportunity. While you're thinking, I just wanted to ask one thing, well, for you to comment on later. It seems that the work that you're referring to is mostly in the medical and pharmaceutical fields, but a lot of this sort of modelling is done in the social sciences, and I wondered if there's any different considerations that you would need to deal with that sort of you could say some of it's a bit more vague data, less rigid than some of the medical research that is applicable here. So it's just a comment. So anyone else? Yes, please. Can you say your name and affiliation?
Can I just speak from here?
Yes, well, come up here if you want to. Yeah. Thank you. You don't mind?
No. Okay, I'll pass.
Yes, up to here. So, thank you. 5 minutes.
I have a very brief question. I'm not a specialist. I work more on Granger causality for time series. We work with distributions all the time. Often it's not easy to have data which will allow us to estimate distributions. Is it possible to work with, say, just first moment or first two moments, and that will link up with Granger causality, such as summary measures of the data rather than whole distribution? That's all. My name is Raj Bansali. I'm at Imperial College, and I'm also an emeritus professor at Liverpool University.
Thank you very much. Okay, any other comments? We don't actually have any written comments, actually, so this therefore brings us to the end of this part of the discussion meeting. I'd like to call on the authors to reply if they wish. It's entirely optional. You have up to 10 minutes, but of course you have the opportunity to reply more fully in the actual published version.
Okay. Yeah, thank you very much. That was really great to get these comments from the discussants. Very interesting. And thank you so much for putting in the effort to make these comments. So Sean was saying that we don't need the rejection sampling anymore. Is there anything that we can still use from the rejection sampling? I like the idea that it was the opposite of doing the inverse probability weighting, which we didn't actually explain in the paper like this, but it's really quite a nice way of putting it. Do we still need it?
Yeah, and I think in some ways the inversion method, at least as is currently formulated, isn't completely free from problems. So the interpretation gets a bit difficult if you want to specify parts of the distribution of the covariates conditionally on other covariates. So then there's the question of which quantile you should be putting into your copula, because if you want the marginal specification, then in principle you have to sort of do lots of simulations to figure out what the marginal is, and then just take the sample to get the true marginal from that. And I think Sean and Ruth have something along those lines in their paper with the H function. So it's not completely solved yet, but I mean, I think, provided you're willing to be a little bit flexible about the nuisance models you're specifying not being so easily interpretable as they are with rejection sampling, I think it works very well. So on Sean's point about, isn't it easier just to specify the joint distribution of the z's, I'd say yes, it is. But you can still do that with the Vine copulas, because all you have to do is say, when you're parameterizing the bits to do with z, you just say all these are independence copulas. So there's no dependence parameterized in the Vine copula for the z's, so you don't double count. And then you just have the y's afterwards being conditional on you look at the first z, and the second z conditional on the first z, and so on. So that problem is fine with Vine copulas. There's no issue there.
About Ricard, do you want to say anything else for Sean? Or? I would move on.
I think that's good.
Okay. So Ricardo commented on or put forward the proposal with the structural causal models with the potential outcomes as our error terms, and this has been discussed and also motivated. Structural causal models has been discussed like this before, because mathematically people take this as an argument that mathematically the structural causal models can always be written like this. I feel a little uncomfortable with this. I prefer to actually think of something, if we use error terms, of something that is being represented by these error terms. But I myself can't quite put the finger on this, why I feel uncomfortable, so not fully put the finger on why I feel uncomfortable with this. But I can say about the instrumental variable models that Ricardo mentioned, there is also literature already quite a long time ago that people have tried to simulate from certain instrumental variable models that are being used to identify and estimate causal effects with instruments. And it has been difficult in the case of logistic and Cox instrumental variable models, so with a time to event outcome. And there have been some progress has been made to do this. And I think that it's therefore interesting that we could, people wanted to simulate from these models. And if they want to simulate, they can use the Frugal parameterization for this, even though it is going to impose more structure than maybe leaving the unobserved variable completely unspecified.
Yeah, I mean, I would say for the IV model, if you have a continuous uniform random variable on 0, 1, then in principle you can simulate anything you like. So you just have to have very complicated functionals for the distribution of y given x and the distribution of x given z, if you want to do that. Another thing I'd say, Ricardo, is that you sort of talked about how you could parameterize other bits of the distribution to be causal. So you had B with potential outcomes in A. Obviously, we can do that as well, because we just say you have to parameterize the past, and you can do that any way you want. So that would be the distribution of A, L, Z, and B. So you could do that with a Frugal parameterization as well if you wanted to, and we call that the recursive Frugal parameterization. I was also interested, I'm not sure whether we were supposed to ask questions, but maybe the mediation method could be done with your approach if you did allow for the cross-world potential outcomes. It would be interesting to understand that.
Okay, then Richard, thank you very much for the comments, and I really like the idea of the density ratio, because I know this from other work that I have been doing and other people have been doing, and I think maybe there is something in there, that there's more generality in using this, but yeah, it's maybe also a little bit less intuitive from my point of view. Anything that you want to add?
No, I mean, I was a bit curious when you said it was identifiable from P star as well, because isn't the point that you've removed dependence in P star? So I don't see how you would add it back in to go back to P.
Not obviously, but just because you can identify from P.
I don't know whether you're allowed to speak. J'accuse, and you can't respond. And then so
Ilya is worried about the copulas. When I said we can't use the observations, it's when we have continuous z and y in that case, or if one of them is continuous. In principle, you can specify observation type functions also for the continuous case. But it becomes difficult, for example, the usual fitting and or using these observations is not easy in this case. I don't know about this work with the extra Markov assumption.
Yeah, so I think you're talking about I can't remember what they're called, maybe Ricardo would remember. There's a sort of paper where using CDFs to parameterize models, and you get these extra context-specific conditional dependencies. But so I would say Scar's theorem basically tells you that actually copulas are completely general, because any bivariate distribution can be split into 3 pieces, the 2 margins, sorry, any jointly continuous bivariate distribution can be split into 3 pieces, the 2 continuous margins and a copula function. And conversely, any distribution you can write could be written as a continuous copula function and then a possibly truncated marginal distributions. So there is no loss of generality in using a copula, and any joint distribution can be simulated using a copula, provided you choose the margins carefully. I think that was all I had to say to Ilya.
Yeah, okay, so then we had a brief question from Sheila about what in the social sciences. And of course, there are many applications also potentially in the social sciences. I think medical or epidemiological applications are very typical, because that's really about when we want to do something or give advice, like treat a patient repeatedly, patient with a chronic disease or so, or recommend certain lifestyle changes which will need to be sustained over a certain period of time and things like this. In the social sciences, and you could imagine in psychology or so similar settings, traditionally the models there or the approaches there don't like the conditional exchangeability assumption. So basically assuming that we have a sufficient set of confounders, and in this case, time-varying confounders. So they often use other approaches with natural experiments, with regression discontinuity designs or interrupted time series. They prefer that over the assumption, so traditionally, right? But if we were in a situation where we do believe in the that we have sufficient measured confounders to adjust for this time-varying confounder, then we could use the same approach in those contexts.
I would also say I have worked with a guy in the Social Policy Institute in Oxford who's interested in sort of survival modelling in development contexts. So sort of when you've got social interventions over time, like a cash transfer, for example, what the effect is on some particular outcome, like teenage violence, for example. So these models certainly are used in the social sciences, and I can readily imagine that they might be applied in that context as well.
Yes, and then at the end we had a question about what is the relation to Granger causality and moments. With the Granger causality I can say a little bit about, because I briefly worked on this, but in the time series context, it's this conditional specification is very obvious. It's always this time point given what was before. We once had a paper, a collaborator of mine, co-author Michael Erkler and I, about how to express, if we intervene here in a time series that is specified in the usual way, on the effect at some later point in time, using the G formula. And we could have done this also with inverse probability weighting and posited a marginal structural model, but this has not caught on at all in the time series literature. So I'm not aware that this has been continued or found much interest there. Do you want to say something about the moments? If we just...
Yeah, I don't know how one would do it with only the first two moments.
Yeah. Okay, that's as much as we can say. Thank you very much again.
Thank you.
Okay, just before we close, I'd like to say something about the next discussion meetings, if you don't mind. The next one will be on the 6th of December here and also online. And it's a Series B paper called Root and Community Inference on the Latent Growth Process of a Network by Crane and Zhu. Generally speaking, full details of discussion meetings are available on the RSS website and announced in members' newsletters and on Twitter, ex-Twitter. And if you'd like to be informed personally about discussion meetings, then please send a message to Judith at journals@rss.org.uk, because there is a distribution list that you might like to be part of. So at that point, I think this closes this meeting. I'd like to thank all contributors, but before I do, I'd just like to mention that we do, up in the lecture theatre, we have some refreshments, and I hope that your people who are here will join us upstairs after this meeting. But thank you again to the presenters.